So today we are going to start with dynamic programming. Dynamic programming is one of the most crucial concept of algorithm. It is used to solve optimization problem. Okay, whenever there is find something maximum, minimum, or shortest or longest, this type of terms appear. So that may be a optimization problem. Optimization problem can be solved in many ways, and one of the most efficient way is dynamic programming. Okay, so what dynamic programming do? It use recursion. Okay. As I am telling in every lecture that recursion means you have to write good recursion. There can be good recursion, not so good recursion, like that. If you are writing very good recursion, then dynamic programming, complexity of dynamic programming can be reduced very much. Okay, we can write good program for that. So what is the definition of dynamic programming? If you look at the dynamic programming approach, then there are few steps, like it used to solve optimization problem, and it use recursion, break the problem into sub-problem, and combine the solutions of the sub-problem optimally. Okay. Whenever there is recursion, there should be some stopping condition. So before going to more inside the theory, let's solve a problem first, and you will have a clear idea how we actually do this. Okay. We do this with the recursion plus memorization. As I told in the lecture of Fibonacci sequence, we use recursion plus memorization and write the recursion which looks like top-down tree, but we solve this problem using bottom-up approach since we have memorization. Okay. Now today I am going to solve this problem, shortest path problem, which you people already know. Shortest path problem, you have used Dijkstra algorithm in graph algorithm section to solve this shortest path problem. Now we will solve shortest path problem in DAG. DAGs mean directed acyclic graphs. Okay. So suppose we are given a directed acyclic graph. Directed acyclic graph means it will have direction for every edges and there will be no cycle. Okay. So that is directed acyclic. So let's say I have taken this example. A small example, A, B, C, D, E, F. These are the node, and I have taken this weight randomly, not randomly, in order 1, 2, 3, 4. Then again 1, 2, 3, 4. Okay. You can choose any other weight also. That does not matter. Now, first thing we are going to do with this, we will represent the graph in a linear fashion. Linear fashion means we will draw it in such a manner that all the edges should look like left to right. Okay, we can easily do that thing. Let's say we have A here, C, D, and E. Okay. So F must be the last node. Okay. So let's assume the shortest path problem is there will be some starting point and there will be some destination target point. But we can generate all pair single source shortest path problem. So assuming A as the source vertex, and for all other vertices we can compute the shortest path. Okay. So let's write the last node here, F. F can be reached from two places. It can be reached from D, it can be reached from E. Let's say this is our E. So this edge weight is 3 and this is our D. There is an edge from D to E which has 2 edge weights, and D to F. D to F edge weight is 3. Okay, now We have other edges. This is, let's say, B to D is 4, and we need to draw one more. Okay, this is C, this is A. Now A to C is 2, and A to B, it is 1, and C to B, it is 3. Okay, have I drawn all the edges? 1 2 3 4 5 6 7, 1 2 3 4 5 6 7 8. One more edge is there. D to E I have drawn, C to E I have not drawn. Okay, so there is one more edge, C to E. C to E is 1. So now this graph is drawn again in linear fashion. So you can use topological sorting for that, or you can check the edges to make it in this way. Now let's say we have to, this is our starting point A, and we have to solve the problem for all other vertices. Okay, all other vertices means we have to find out shortest path from A to C, A to B, A to D, A to E, and A to F. Okay, we want to solve this problem using dynamic programming. Okay, we already know the concept of Dijkstra algorithm, and we can solve it easily using Dijkstra algorithm. Let's do it using dynamic programming. So first step, I have to write a recursion. This is an optimization problem. Why? Because this is shortest path problem. So it is an optimization problem. Okay, we have to find shortest path. So let's write a recursion first. Recursion is, let's say, let's put some name to the problem for the function. Okay, shortest path problem. In so let's write SP is the name of the function. Okay, and we have to compute the shortest path. Let's take the last point first. We are writing the recursion for the point F. Okay, shortest path at F. Every time the starting node is A, so I am not writing A. A is fixed for all the vertices. So this is our program, shortest path at F. We have to write a recursion for that. So whether we have to maximize the thing or minimize the thing, we have to find out shortest path. We have to find minimum. So let's write min. Okay. Now recursion. Now from how many node, we will look at the last step. How f can be reached. What are the possible previous nodes? So there are two options. It can be reached from D or it can be reached from E. Okay. So I am going to write shortest path at F. If I know shortest path up to E, then and it is reaching from E to F, then what will be the value? We can write shortest path at E plus the cost of last edge, which is 3. Or do you have other option? Yes, I have other option. We can write shortest path at, what is the other option? At D plus, here is also the edge weight is 3. D to F was 4 in the original diagram. So let's make it 4, and this is 4. Okay. So this is our recursion. What is the stopping condition? Shortest path at A is 0. This is the starting vertex. So at this point, shortest path value is, so I got the recursion and the stopping condition. Now I can solve it. If I write, if I directly call this recursion, it will create a long tree where there will be repetition. So that will be a costly recursion. we will not go for that. We will use a memorization stack. Okay, memorization stack means we have to compute. This is our memory. Okay, not stack. This is our memory. Here we need all this value. SP at A, which is 0, we already know. Now I want the other values. SP at next node is C, then SP at B. Okay, in this way last one will be SP at F. We have to return the path also, so I will show you how to do that. And we will compute these things in bottom up manner. Every time we will call some recursion, the sub recursion sub problem will be look up in the table and the value will be uh, put directly. Okay, so there will be no repeated computation of the same sub problem. That was the purpose of making it linear. Okay, now let's solve it. First node is SP at C. What will be the option? Use the same recursion. Okay. So SP at C can be written as C can be reached from how many nodes? There is only one option A. So we have the same recursion mean, and then SP at A plus the cost of this A to C 2. Is there any other option? No. So minimum value is itself. So this is actually, we will get, what is the value of SP at A? It is 0. So 0 plus 2 is 2. Okay. We will return one more thing. What? We will return in which path we are reaching this thing. Okay. We have to compute SP at C, from which path uh, we have to return the path. So I am going to return this thing also. 2 is the answer and we will return A also. Okay, so let's not write here. Let's put 2 is the answer. I am returning A here. Okay, now compute the similarly SP at B. What will be its value? Its value mean again. How many option is there at B? There's two option. SP at A, it may go from A plus 1, and second option is it may go from C plus 3. Okay, clear? Now what is this value? 0 plus 1, 1, and SP at C, we already computed SP at C, that is 2. So we are not going to compute it again. We will look up the table and put the value 2 plus 3, 5. So we have minimum between, sorry, not 0, it is 1, 1 and 5. Okay, so what is the minimum value? Obviously 1. So I am going to write it here 1, and from which vertex, which option? We are getting this from this option, so we have to return A also, so that we can indicate the path. Now similarly compute other values. SP at, we have computed up to B. Now we will compute D. SP at D. D can be reached from only one option, so we don't need to compute minimum. Okay, so and we can directly compute this SP at B plus 4. So it's this is equal to 5. Now SP at D equal to 5. So let's write it here. Shortest path from D equal to 5. From Which vertex it is coming? B. So we will written B here. Okay. Now we have to compute more thing. Next one is shortest path at up to D we have computed. Now we have to compute E, minimum of. We have two options for reaching E. It may be from D or it may be from C. So SP D plus, if we reach from D, we have the last edge is cos 2. If we reach from C, then last edge is cos 1. Okay. Now SP at D, we already know. Look up the table. This is 5. 5 plus 2 is 7. SP at C. SP at C is 2. 2 plus 1 is 3. Minimum is 3. Okay. So SP at E is equal to 3. And from which option? It is coming from C. Okay. Now we have to compute one more shortest path at F. Okay, we already have these things, so let's put the value. Now we know SP at E. What is the value of SP at E? It is 3. 3 plus 3 6. And SP at D, its SP at D is 5. So 5 plus 4 9. So which one is minimum between 6 and 9? 6 is minimum. So we are going to choose this. So this value is, let's write it here, 6, and we have to return the option it is qualifying from E. Okay, now we got the path for everyone. E can be reached from, okay, so let's write path from all. A has no path, A is itself, and B can be reached from, B can be reached from, where is SPB? It can be reached from A. Okay, the minimum cost here is 0. B to A is cost 1. Okay, and C is also, it will reach from A. The path is AC. Okay, this path is AB here. The cost of C is 2. We already computed that. D can be reached from, let's look at the D table. It can be reached from B, and B can be reached from A. We already know that. So, and the cost of D is 5. Okay, so this is the path and this is the value. Now we have to compute two more paths for E. E will be reached from C, and C was from A. The path was, cost was 3. Now F was reached from E, and E reached from C reached from A. Cost was 6. Okay, now solve. We got the shortest path for all the vertices, and we got the path, we got the weight. Okay, so we got both the things. Now this is shortest path problem using dynamic programming. Now what the things that we have done, let's once again we can relook. Given a problem was shortest path index. Okay, directed acyclic graph. So this is the thing associated with the problem. You have to understand the problem, you have to properly represent the problem. So we are representing here with a linear representation. Now you have to write a good recursion. So this is the recursion. Every time you are thinking about recursion, how to think? You think about the last step, how the last step can be solved. So F was the last step, we have to reach at F. F can be reached from two options. Okay, there was two options. So now write sub problem in this way. I have to solve only the last step. All the previous value I already know. Think about it. Think like that. Okay. Then you will be able to write the recursion. So the recursion will be this and it will be solution. And in every problem, we'll think in same way how the last step was solved. And we will write the recursion, but we will never compute the recursion tree. We will go for memorization with the help of memorization and compute in a bottom-up approach, not the top-down approach. Okay, that's all. Next, meet in next lecture with some other problem.